Okay, hey, welcome back, class. We are starting to work on Unit 2, just a continuation of our last few lectures. Today we're going to start talking about ions and isotopes. So just a refresher, what we've been talking about are subatomic particles, and we've talked about the atoms are made up of protons, neutrons, and electrons. In the neutral atoms, the number of protons equal the number of electrons. In order to find the number of neutrons in an atom, we're going to have to take the atomic mass and subtract the number of protons from it. Today we're going to be talking about what if this is not the typical situation. What if it's not neutral? What if we have more neutrons than a normal atom? So let's talk about our roadmap for today and our objectives. So our first objective is to be able to determine what is an isotope and what is an ion. And then we need to be able to determine the number of subatomic particles in each one. So basically, if I give you an isotope of carbon-13, you got to be able to tell me how many protons it has in it, how many neutrons it has in it, how many electrons it has in it. Or if I give you an ion such as calcium-2+, same thing, protons, neutrons, and electrons. In order to do that, we're going to have to learn some stuff about them. So let's dive on in. So what we need to understand first is that atoms can vary. We all know that the number of protons are the identity of the atom, so we can't change that up. So no matter what, my carbon's always going to have 6 protons because its atomic number is 6. Okay, if I added a proton or subtracted a proton, that's going to change the whole element as it is. So we need to understand that with this varying in atoms, it's not going to change the protons. So protons not going to change. That means it's either going to be the electrons or the neutrons. With these changes, also change the behavior of an atom. So basically that means like, okay, if I add a neutron to this atom, it's going to be a little bit more unstable, so more likely to react. Or if I add an electron or take away an electron from an atom, same thing. So we need to understand that by adding and subtracting electrons and neutrons, we're also changing the stability of the atom and how it interacts with its environment and other elements. So let's talk about atomic mass. Atomic mass is the estimated mass of an element by adding the number of protons and the number of neutrons. Okay, this isn't as exact. We'll get into the more exact version later. But what you need to know is the atomic mass is protons plus neutrons. If you remember from our last video, if you look at a periodic square on the periodic table, the decimal number at the bottom of the periodic square on each element, that's the atomic mass number. Okay, that's going to tell you how much mass this atom takes up. Atomic mass is expressed in AMUs. Okay, so like instead of grams, centimeters, or anything like that, when we're talking about atomic mass, we're talking about AMUs. That's atomic mass units. And as I stated earlier, this is more of an estimate. Okay, it's less precise than finding the exact number. So remember, if we're taking anything from this, atomic mass is found at the bottom of each periodic square. It's that decimal number and it's the number of protons plus neutrons. Okay? So let's start off talking about isotopes. So the big thing of isotopes is the change in the number of neutrons in an element. So you might have many forms of an element. So we can have carbon-12, carbon-14, carbon-13, carbon-11. All these different forms of an element, and they're going to have different atomic masses. Well, if we remember, our protons never change, and our protons plus our neutrons are going to be our atomic mass. So if protons never change and the mass does, then that means the number of neutrons are either going to be added or subtracted. Okay? So this change in the atomic mass and the number of neutrons is going to change our properties of this element. So isotope, big thing. Different number of neutrons in the base element. So when looking at an isotope, how do we know if we're looking at one, first of all? Well, there's 2 types of forms that we're going to go through. One of them is going to be paired with the atomic symbol, while one of them is just going to be longhand written out. So let's talk about the longhand version first. You're going to hear something like carbon-13. It's going to write out carbon-13. That 13 is saying what the mass of that carbon is. So we come in there and we think, okay, well, it's saying specifically it's a mass of carbon, so that must mean it's not a normal atom of carbon. So we go look at our periodic table and we see In fact, the normal atomic mass for carbon is 12. Well, we're stating here that it's carbon 13. So what does that mean? That means we have an isotope. Okay, if protons never change, that means it's only neutrons that change. So we got to figure out how many neutrons are in this. So we take our atomic mass, the 13, and we are going to subtract the atomic number, or the number of protons from it, and that is 6. So that's going to give us our number of neutrons, which is now 7, opposed to a normal 6. So that's one form of isotopes. Another form you may see is two numbers, one a subscript, one a superscript, next to the chemical symbol of an element. Okay, let's get the obvious out of the way. The chemical symbol is the representation of what element it is. Then the superscript number, the top one, that is going to be the atomic mass, the new atomic mass of the element. While the bottom number is saying the number of protons that are present in that element. So for instance, if we're going back to our carbon 13, okay, that's going to have a 13 as the superscript, a 6 as the subscript, and then a C. Okay, and that's still going to be our carbon 13, another way to write our isotope. Now that we got through isotopes, okay, now that we understand that it's a different number of neutrons, okay, we can start talking about the precise way, more exact way to find the atomic mass. This is the average atomic mass. The average atomic mass takes up not just the typical form of an element, but it also accounts for the atomic mass of isotopes and their abundance in this world. So the atomic mass is more precise, or gives us more of an accurate rating of what all the atomic masses of this single element there is. So for instance, let's take our carbon 13. There might be 80% of regular carbon, carbon 12, and 20% or whatever the remaining percentile is of carbon 13. Okay, obviously our carbon 12 is going to take up more weightedness than our carbon 13 because of its quantity. And that's how we account for that with the average atomic mass. So let's go through the formula with this. So your average atomic mass equals your percent abundance of that element. So in these problems, you're going to get, hey, we have 73% of the carbon in this world is carbon 12 or something like that. So you have the percent abundance of that element, and you're going to multiply that by its atomic mass. So there's one portion. Okay, and then we're going to add that to another portion, and that's going to be the percent abundance of the next set of element times its atomic mass. So for instance, if we have 80% carbon 12 and 20% carbon 13, it would be 80% times 12 plus 20% times 13. Now here's a key note here. Whenever I'm talking about these percentiles, I want you to understand that you can't just put 80 times 12. You need to make these into a decimal number. So 80% equates to 0.8. Okay, and 20% equates to 0.2. That's going to give you your accurate rating, or your accurate mass of them. You will do this for as many elements as it lists in their percentiles. Sometimes it might be only 2 isotopes of an element, while other times it might be like 5 isotopes of an element. It doesn't matter. All you need to do is just repeat this process for as many as there are. So for instance, here's at least one practice problem we'll have in this video. We'll have a whole video of working practice problems later. Chlorine consists of 2 major isotopes. The first one is chlorine 18, which percent abundance is 75.77% on this earth, while the other isotope is chlorine 20, which is found at 24.23% abundance on this earth. We need to figure out the average atomic mass. So what we're going to do is, first of all, convert our percentiles to decimal numbers. So our 75.77% turns to 0.7577. And then we're going to multiply that by their atomic mass. So we have 0.7577 times 18. That's going to be your first section. That's going to be 13.6386. Okay, I'm going to turn my phone sideways. Then we're going to add that to our second set of multiplication elements. So we take our 0.2423 times our 20, and that's going to give us 4.846. Once we add both of those together, we get 18.4846, which should be your average atomic mass. Now let's start talking about messing with electrons. So ions is what messes with electrons. Okay, remember, a neutral element has the same number of protons and electrons. Well, our ions are not neutral. They are charged particles. Okay, so these charged elements or charged particles have an overall charge that's not neutral, meaning you're going to have more or less electrons than protons, depending on what the overall charge is. So what causes these charges? Let's talk about that. Remember, protons never change. That's the identity of the atom. Okay, so we're always going to have that number of protons for that specific element. But our electrons can change. So that means, okay, if I am taking away electrons, that means I'm going to have more protons than electrons, so the overall charge of the atom is going to be positive. Or vice versa, if I add more electrons, that means it's going to have more electrons than protons. It's going to make the atom more negative. So if I add electrons, it makes the element more negative. While if I take away electrons, it's going to make it more positive. So keep that in mind whenever we start looking at these ions. So ion form, what do ions look like? Well, basically you're going to see a chemical symbol and a plus or minus number as a subscript. If it just has a plus or minus, that's just 1. But if it has a number with it, then we know it's plus or minus 2 or plus or minus 3. And we know how many electrons are going to be in that element just by that information. So remember, if I'm adding electrons, it's going to be more negative. So if I see chlorine minus 1, okay, that minus 1 indicates that it has 1 more electron than proton. But if I have calcium plus 2, that if I have a positive number, that's going to say I have more protons than electrons. So that means I have to take electrons away because protons never change. So that means it has 2 more protons than electrons. So I lost 2 electrons from its base or neutral state. Just some verbiage to throw at you: cations and anions. Okay, if it's positive, so if we have a positively charged ion, that's going to be known as a cation. While if it's negatively charged, that's going to be known as an anion. How I like to think of this, you have the T in cation. Okay, that looks kind of like a plus sign, so I kind of correlate that to positive. While if you have anion, you see you have a lot of N's in it. That's going to be more negative, so it's going to have the negative sign. Or if you really like cats, you can say cats are positive and ants are negative. Okay, so cation, anions. That's all I got with you on this. That kind of just breaks down these ions and isotopes. I will have practice problems that go with them. I hope this helps you out, and keep up the good work. See you next time.